All right, in this video, we're going to look at chemical equilibria and positions of chemical equilibria. So let's first describe what an equilibrium is. And I'll do this through one of my favorite examples, where you can take water, which is obviously a liquid under standard temperature and pressure, and you can expose water to CO2 gas, right? So carbon emissions from combustion, CO2, most people are familiar with that, right? But what a lot of people don't know is that when you mix water and carbon dioxide, you create an equilibrium where you end up creating something called carbonic acid, which is H2CO3. And as you can imagine, carbonic acid, by definition, is an acid. So a lot of people have been talking about CO2 as it relates to climate change, right? So the warming of our overall global atmosphere on average, right? But what a lot of people aren't talking about that's equally concerning is if we keep on adding CO2 into our atmosphere, we'll be creating more and more of this carbonic acid in our waterways, specifically our oceans. And when this happens, our oceans get more and more acidic, and that creates a whole host of problems for the organisms that live within the ocean. If you are interested in reading more about the ecology behind that, it's fascinating and it's terrifying, but it's something that I think we should all be informed about, especially since we live, on the Puget Sound. So when we look at this, we've got this unique set of arrows here. This essentially means the reaction can go either forward or it could go reverse. So in the forward direction, this is just a combination reaction. But it's not that all of the water is going to react with all of the CO2 in the atmosphere to form exclusively carbonic acid, right? Because we have this competing reaction that also takes place at the same time. So just as we're forming some carbonic acid, some of it is going to decompose back into, water and carbon dioxide, right? So here's the weird thing, is that at equilibrium, all three of these are present. So if we were to look at this as a reaction mixture, we'd have some carbonic acid, we'd have some CO2, and we'd have some water, all floating around doing this dynamic forward-backwards reaction, right? So that's one important thing, is that both the forward and reverse reaction take place. That's the whole idea behind an equilibrium. So let's define it in some different terms too. So the book calls this a state of equilibrium. Most people just say equilibrium, they don't say the state of part. So same idea. But what it means is it's a condition where the forward and reverse reactions are occurring at the same rate. Where the forward and reverse reactions are equal. So if we go and we look back at our previous example, right, we could say, well, the forward reaction was combination. That would have one rate. The decomposition would have a second rate. And when those two rates are equal, basically things are happy, right? We've created a situation where there's balance between the forward and reverse. That's called equilibrium. All right. So again, let's describe what's going on here. Well, when you're at equilibrium, you've got what is called an equilibrium concentration. And what this means is it's looking at the concentration of each component of the mixture at equilibrium. And at that point, things basically stop changing in terms of their overall concentration. There's still forward and reverse reactions going on, but the net change is zero, right? So the concentration isn't going to be affected. So it's the unchanging concentration of reactants and products in a reaction at equilibrium. All right, so I know when I learned this, I was very confused. So I've got a good visual representation of what's going on here. So let's do an example. And the site I'm going to be using is called a PhET simulator. And what we're going to do here is we're going to imagine a scenario where we just have two components in solution. We're going to have A and B in equilibrium, right? So A is getting turned into B a little bit, but sometimes B is getting turned back into A. So let's imagine what this looks like using this PhET simulation, and I'll put a link in our Canvas module as well. All right, so here's our PhET simulation, and it's a little hard to see, but we've got reactant A over here, and then on the other side we have component B. So A can turn into B, and B can turn back into A. A is a little less stable, it's higher in energy, therefore it's got a higher platform. B is a little bit more stable, so it's down here on a lower platform. This little hump, if you remember, is our activation energy. So the molecules have to have enough energy to get over that hump before A could turn into B. Conversely, B would have to overcome this hump to go back to A. So let's go ahead and add in 100 of these A molecules. So I'm just going to go ahead and add those in, and they're just going to pool up in the A side. And at room temperature, some of them will have enough energy to actually move on over to that other side, right? So this is just room temperature, but let's try to give it a little bit of a boost here. So I'm going to add a little bit of heat. We'll heat it up to about there. And as you can see, we still have mostly A, but we're making more and more Bs as time goes on. And in fact, you can see this over here on the right-hand side. It actually has a live count of the number of A atoms and the number of B atoms. But let's imagine over time, right? B is actually lower in energy, so we would predict that more of the balls are going to end up on the B side because they're going to have a harder time jumping over the hump to go back to A, right? Because that's a bigger hill to get over than A going to B. So let's just keep this going for a while and see what happens. All right, so we've let it go for a while, and now you can see we've actually got more B's than A's. And when we reach a state of equilibrium, the number of balls on the A side is essentially going to remain more or less the same. Same thing with the B side. At equilibrium, yeah, some will be going back and forth, but the net impact will remain unchanged, right? So if I look over here on this side, it looks to me like it's kind of hovering right around 59, 60 Bs and about 40 to 41 As, and it's just kind of hovering there. Yeah, it might vary by like 1 or 2, but essentially we're at an equilibrium concentration now. So we can see that 60% of the equilibrium is going to be on the B side, more or less, and about 40% is going to be on the A side. So this gives a good idea that it's not static, right? Things are bouncing back and forth, but we're looking at when things essentially stop changing, meaning the amount of B balls remains roughly 60 during the overall time. So let's imagine modeling this on a graph, right? So over here on this side, we've got concentration on this axis. And we said originally we had, 100 of our A molecules right here. So I just call this A. And then down here, we said that we had 0 of our B molecules. So I go ahead and write B down here. Well, over time, we saw that the A concentration dropped and then essentially plateaued. And then B, on the other hand, did the opposite. So this down here is time, And we would ask ourselves, well, when are we at equilibrium? Well, I would say it's when the concentrations stop changing. So right here and right here, this is equilibrium. So no net concentration change. Therefore, this is when equilibrium occurs. It's essentially at this point. So this whole section would be at equilibrium. All right, I hope that makes sense. I know it's a little hard to imagine in your head, but I find that PhET simulation kind of helpful. So if you want to play around with that, you're welcome to. All right, so let's go to the next part. The next part is looking at the position of the equilibrium. All right. And the position of the equilibrium kind of relates to that PhET video that we just looked at, right? So in that video, we saw ultimately we ended up with more B's than A's, right? So a position of the equilibrium kind of looks at which side do we have more of. So it's an indication of the relative amounts or concentrations of reactants and products at equilibrium. All right, and we can study this a fair amount. So let's give an example. And this one's going to look a little bit funny, but let's imagine that we've got reactant A reacting with reactant B, and so on. And this is going to be in reaction or in equilibrium with W and X and maybe some other things. Well, the first thing we always need to do with reaction is balance it, right? So I'm just going to go ahead and put these numbers in, or these letters in here that will represent our reaction coefficient numbers. So remember, you always need these for a balanced reaction. Well, let's take a look at the equilibrium expression. This is essentially a mathematical model of what's going on. And let's use this above reaction, right? So what we do is at equilibrium, we know things are going to remain static. So we call this K, capital K, our equilibrium constant. All right, and we can solve this by taking the ratio of our products to our reactants. All right, so we've got our products, one of which is W. However, we need to factor in how many of them there are. So I'm going to go ahead and plug in that reaction coefficient as an exponent right there. And then the same thing with X. We're going to multiply the concentration of X in and multiply it by its reaction coefficient. And then on the denominator, we'll do the same thing with A and B. And it's important to remember that we have to use the reaction coefficients from the balanced reaction. So it'd be A and B here. The other thing to remember is in these equilibrium expressions, these brackets right here equal concentration. And the concentration that's used is molarity. All right, so you can do this for a given reaction. You can identify the concentration present at equilibrium, plug in the appropriate reaction coefficient, and solve for your equilibrium constant K. All right, so let's do an example here. So let's do a reaction where we've got two sulfur dioxide molecules, they're gas, reacting with oxygen, which is a gas, to make sulfur trioxide. And in order to balance it, we need two of them. Okay, so let's calculate the equilibrium expression here, or at least write it out, I should say. Well, on our product side, we've got SO3, right? And then we've got a 2 as our reaction coefficient. So I would put my SO3 in brackets. We need to find the concentration of that. And we need to raise it to the second power because of that reaction coefficient. And then on our denominator side, I would want to include these two components, and then I'd want an exponent 2 next to the SO2. So let's go ahead and put SO2 here, raise it to the second power, put O2 next to it. It's raised to the first power, but we don't need to draw that. All right, hope that makes sense. It's just a basic mathematical model of our equilibrium concentrations, right? But let's imagine, right? If K is large, what does that mean? So if we calculate K, and it's a number, let's say, in the billions, well, that tells me that the numerator side must be massive, right? It must be a lot bigger than the denominator. Conversely, what that means is that the reaction, or that the equilibrium, favors the right-hand side. And I'm going to put product in here. I don't really like calling it the product side, but we're used to seeing products on the right-hand side anyway, so I call it the product side. Conversely, if K is really small, let's say a tiny, tiny, tiny fraction, then that means that the equilibrium favors the left-hand side. And I'm going to call this starting material. And we'd have a much higher concentration of all of the components on the left-hand side of our equilibrium. In fact, if K is so small, that means that the reaction is simply not going to take place, right? If K is enormous, let's say you're talking about like 10 to the 50th power, that essentially means that the reverse reaction is tiny, meaning you wouldn't have really any of your remaining starting materials left, and it wouldn't even be an equilibrium anymore. But that's neither here nor there. Equilibria, in theory, exist for every reaction. However, there becomes this realm of practicality where the reverse reaction just is so improbable. The reaction's really not under any normal equilibrium conditions. All right, I hope that helps, but let me know if you have any questions.